Okay, so we now have three laws, and let's see if I can grab a color that we'll see on this bright blue screen. We've got Boyle's, which is the P1V1 equals P2V2. We've got Charles's, which is V1 over T1 equals V2 over T2. And we've got Gay-Lussac's, which is the P1 over T1 equals P2 over T2. Now you're probably noticing that there's some similarities and that we might be able to combine these. And so we certainly can do that. The combined gas law is taking these three laws and making one. Okay? And as you can see, when the pressure and volume, they're both on the top here. They're both in the numerator. Notice the volume and pressure here. Whereas temperature is in the denominator in this case. So the combined gas law is pretty straightforward. It is, you're combining the pressure, temperature, and when they don't remain constant. So you can see that we had in Boyle's temperature constant, in Charles's pressure constant, in Gay-Lussac's temperature constant, volume constant. If they don't remain constant, if all the variables change, then we can use the combined gas law. And very simply, the combined gas law is P1 times V1 over T1 equals P2 times V2 over T2. And notice that really we've got Boyle's law, right? We've got V1, P1 equals P2, V2. We've got, if I cross out here my P's, I've got Charles's law. Or if I cross out here my V's, I got Gay-Lussac's. So I like to really say, rather than remembering three other laws and three formulas, if you remember this one law, and if the problems that you've got to solve, or if you notice that you have something, one of those variables that remains constant, ignore it. So if you're reading a question, it says the pressure, the volume, the temperature, and then it changes the pressure, what's the new volume? If the temperature remains constant, just cross it out and you'd be using Boyle's. Okay? So let me show you an example, and here's where, again, I haven't done any real big calculations, but let's say that I have a situation where, I don't know how well we can see that black. Let's go to a different color. So let's say we have our pressure in the first situation. Again, how that would read in a problem would certainly differ, but it could say on Tuesday, Mr. Markey records the pressure of a system to be 1.25 atmospheres. He also notes that the volume is 10 liters and the temperature is 25 degrees, Celsius. I may very well not say anything about T1, V1, but those are the three that go together. If it says now on Wednesday, the pressure has changed to 3.5 atmospheres, what is the new volume? Question mark. Of course, that's going to be in liters. If the temperature has changed to 50 degrees Celsius. Okay, so notice again, it would be certainly very rare if I say ones and twos, or you're ever going to read that, but it would say, in a certain situation, these go together, in a certain other situation, these go together. So there's my formula. I'm a big fan, you know it, when we're doing calculations, when we're solving problems, to take what's given and write what you're solving for. So I've done that. I've written down everything that I'm given, and I've also written down what I'm solving for. I now like to write my formula. So let me go ahead and do that. P1 V1 over T1 equals P2 V2 over T2. I'm a much bigger fan, rather than plugging in our numbers right now, I'd much rather rewrite the equation for what I'm solving for. So I'm solving for V2. I want to rewrite this equation so that V2 equals all this other stuff. If you've seen the other little videos that I've had, I'm a big fan of cross multiplying to get that all cleaned up so it's all in one nice clean line. So P1 V1 T2 equals P2 V2 T1. There's your cross multiplication. Now that I have it all in one line, if I want to solve for V2, which is what I want to do, I can simply divide both sides by P2 T1. That'll cancel them on this side, giving me my volume 2 all alone. So V2, and I'm going to write it pretty big, P1 V1 T2 over P2 T1. Now that I have it all rewritten, let me grab another color here that is easy to see on this background. Let's grab this green. Okay. Now that I have it all written, I'm solving for my V2. I can plug and chug. I can write V2 equals, well, P1 is 1.25 atmospheres. V1 is 10 liters, and T2. Now notice it's 50 degrees Celsius. I cannot put in Celsius. You can never put in Celsius when you're solving the combined gas law. You must use Kelvin. I said that earlier in the chapter. I'm reminding you now, use Kelvin always. One of the reasons is that 0 degrees Celsius is a very, very common temperature. In fact, it's standard temperature. And notice that because temperature is in the denominator of our combined gas law, or our Charles's and Gay-Lussac's, if temperature is in the denominator and 0 is a very common value for it, it would be undefined. You can't divide by 0. Whereas Kelvin, you can never have 0. Okay, that's absolute 0. You can never have 0. So you would never have that 0 in the denominator, making it undefined. You must have your temperature. Even though both of them are in Celsius, you must convert them to Kelvin before you plug them in. So let's add our 273 to both of these. This would be 298K, and this would be 323K. So I'm looking at T2, so that's the 323K over my pressure, my second pressure, which is 3.5 atmospheres, and my my first temperature, T1, is 298K. Now, I don't know how comfortable everyone is with your calculators, but I certainly do like to multiply my top three numbers, write a number. Okay, so 4037.5, and divide that by the other two multiplied together, 1043. Okay, and then when you divide those, you're going to get 3.87 liters, and there's your answer. How do I know that liters is my answer? Well, notice that atmospheres units cancel and Kelvin cancels, and it makes sense that liters is going to be my unit because I'm talking about volume. So there's the combined gas law. You can solve for any of these six variables, again, by just rewriting the equation and solving for the one that you're looking for. There's your combined gas law. And in essence, all the other ones.